So from terms of a class announcements perspective, we pushed our homework due date back till Wednesday. So we should finish up separation of variables today, and then we should be able to do all our homework problems. Then we're going to spend the next probably, well, at least through Wednesday, finishing up on part 2 of the separation of variables lecture. This is some stuff I'm adding on that I think is really important to have on Sturm-Liouville theory, that I think is really important stuff to cover. But I don't have any homework problems I've made up for it, so we're just gonna do that. I'm sure you're all really disappointed that that means that I have a fewer, like a lighter homework load because of that. So we'll just enjoy that material, okay? And then we're gonna move on. I'm actually gonna switch the schedule up a little bit to how it is. I was thinking about this over the weekend. I think we're gonna do boundary layer theory next. So the way the schedule is kind of arranged is a little funky to me. So we're going to do boundary layer theory next, which is sort of another set of kinds of solutions that we solve. And so then we'll have sort of covered the major topics of how we solve these problems. And then I will decide whether we're going to do numerical solutions or not. We probably won't have time, so we probably won't do that. And then we'll sort of go back and take these solution methods and look at some specific problems in momentum, heat, and mass transfer, and see if we can pick them apart and understand. That's probably where we'll finish the class, is my guess, based on what we're getting to. We probably won't have time to get to the interface transport. Interface transport sounds exciting, but I actually think it's really boring. Essentially, what you do is you do dimensional analysis, and you figure out that there's dimensionless groups, and then you write down correlations between those groups, right? Sometimes informed by theory, but not always. And then you calculate things like friction factors, drag coefficients, Nusselt numbers, etc., and then use that to calculate quantities of heat transfer or mass transfer or whatever. Okay. So to me, like, that's good practical engineering stuff. And you guys probably did quite a bit of that actually in heat and mass transfer. I know you did quite a bit of that in fluids because we did a lot of friction factor calculations, and that kind of stuff there will be ideas from that on your qualifier exam. Okay, so you want to review the kind of stuff you did there and think about that in your sort of newly informed perspective. But nothing on the qualifier exam is going to be like graduate specific that we had to sort of cover in that sense. It's all, kind of review from undergrad in that sense. So anyway, so that's kind of the thing. I should also have a little more to say about the qualifier exam on Wednesday. I'm going to have a practice exam for you guys to do and some sheets that tell you all of the material that will be on there. So maybe if you have questions about that, I'm sure you will, bring them on Wednesday. We'll have a discussion. Okay. So that is the announcements I can think of. So let's dig into where we were. So last time, so the time before we had done this semi-infinite boundary problem, right? And last time we said, well, let's do a problem where we have a parallel plate and we have the startup of transient flow. And so we set that problem up and we non-dimensionalized it. And then dimensional analysis was a lot simpler than in the case before. And it just allowed us to get rid of a bunch of constants and have ones. And then we said that in order to do separation of variables, we were going to need homogeneous boundary conditions. So we actually found a steady state solution and subtracted it to get a new equation. And so that was what we did right here. Okay, we found the steady state solution and we subtracted it and we got a new equation. It was actually the same differential operator, but it had different boundary conditions. So previously we had a 0 here and like a 1 on the boundary, and this flipped it so we had homogeneous boundary conditions and a non-trivial initial condition so that we could solve for phi t using separation of variables. Okay, and I didn't justify that here, but I said that we would. And then we launched into part D where we said, let's do the separation of variables. And there's 5 steps in separation of variables, at least how I break it out. You can decide if you like these as the 5 steps or not, but these are the 5 steps I decided. And the first step was to break it into a product solution, to assume it was a product solution. And then in the second step, we carried forward that product solution and separated the variables and set them equal to a constant. And then steps 3 and 4 were to solve each one of these separate ODEs. So in step 3, we solved the time-dependent ODE, and we got an exponential solution. And then and that one was actually pretty quick. This one took a little bit longer. This became a boundary value problem, and we needed to get our boundary conditions, and that's actually ended up being why we needed to have the homogeneous boundary conditions, was so we could apply them to F here. So we then solved the problem here. We got that it was a sum of sines and cosines, and applying the boundary conditions led us to this solution here. And we found out that when we set it equal to 0, that it could have either been, b was equal to 0, or the sign with the constant inside was equal to 0. And so this was a, CN was equal to n pi, right? For n is equal to, what was it? So minus 0, 1, etc. from forever. Okay. And so we found out that there were these special coefficients where it was 0. And if we thought about the sign, that was where all the zeros were. And so that's when that satisfied. So that told us that Cn had, the C had to be n pi, which changed our answer a little bit for G and for F, right? So that now they depend on some index n. So there's a bunch of solutions. Okay. And so that's where we got to at the end of last time. So maybe I'll pause real quick and see if there are any questions about that part, since I reviewed it real quick and it's been a weekend and it's Monday morning, and see if we're all kind of caught up to where we are here.
When you say homogeneous boundary conditions, can you redefine that for me?
Yeah, homogeneous boundary condition is just 0 boundary condition. So 0 on both sides. Yep. Okay, good question. Any other question? That was easy. I could do that one. Okay. So step 5 now is we have a solution, right? If I take and make this FNG, I said that my B was a product of those two. Okay. So I can write, B of t is equal to Gn of t, Fn of t. And just by making a product here, and so that will be an exponential minus n squared pi squared t multiplied by bn exponential n pi y. Okay. Sine. Thank you. Thanks. That was what ChEn was over there worried about. Okay, sine of n pi y. Okay, well, I look at this. These are both arbitrary constants. So I'm just going to combine them to make a single constant. I'll give it a new letter. We've already used c before, so we'll use a d. So this will be d exponential minus n squared pi squared t, and then sine of n pi y. Okay, and this is good for, again, n is 0, plus or minus 1, minus 2, etc. Right? Okay, so this is a valid solution for phi of t. Okay, for phi t, I guess, not phi t at y comma t. That's how I've been running it. Okay, so that's a valid solution, but we don't know if it satisfies the initial condition. Okay, and if we look at it, it sure doesn't look like it satisfies the initial condition, right? Because the initial condition is 1 minus y, and this thing does not look like 1 minus y, right? If I take phi t, at y comma 0, that gives me en sine n pi y. Right? If I put in a 0 for the time right there. So how can I make that, equal to 1 minus y? That's a problem. At least it seems like it's a problem. Okay. So fortunately, if for the case that this equation was linear, okay, This thing is a linear PDE, and these are linear. The principle of superposition applies. Okay, so perhaps you'll remember this from your ODEs class. So if this is a solution at n equals 0, it's also a solution at n equals 1, it's also a solution at n equals 2, but so is the linear combination of any of those. Okay, so I can also write, by the principle of superposition, that Pt is equal to the sum from n equals 0 to infinity. Actually, don't need 0. 1. Infinity Bn of exponential minus n squared pi squared t sine of n y. Okay, that's also valid. I can do that if I want. Okay. Now it turns out that the reason I only go from 1 to infinity here is that if I put in a 0, the whole thing's 0. So that doesn't add anything up to the sum. So I don't need 0. And minus 1 and 1 are redundant. So for a full linear combination, I don't need the minus 1s as well. Okay, because sign is odd, so it just ends up not mattering. Okay, and so to have a solution, I only need this. Okay, so I can go from 1 to infinity of this stuff. Okay, so now what I can do is now apply the boundary. Now let me apply the initial condition. Apply the initial condition. Okay, so I'm going to say Pt at y comma 0. Same thing, put in a 0 here. I'm going to get the sum from n equals 1 to infinity of sine of n pi y should equal 1 minus y. Okay, now those of you who are mathematically astute, which I hope is all of you, okay, but don't feel bad, we're reviewing it, okay? This is Fourier series, right? So if you remember from math, I can make a Fourier series equal, oh, I forgot the most important part here, the n, for me. I can make a Fourier series equal function, right? That was the magic of a Fourier series, is that I can take this infinite sum of sines and cosines and make it equal some function, right? That's pretty awesome. So now instead of trying to equate this to that, which what coefficient can I pick that would make a sine equal to that? Well, instead, I'm going to pick a bunch of coefficients, okay, an infinite number of them, and add up the signs just right so that I can get 1 minus y. Okay? That makes sense? See some staring. Are we uncomfortable with this? Or are we good? So if you're good, give me a thumbs up or nod your head. If you're grumpy or uncomfortable, just sit there and stare at me and then ask me a question in 10 seconds when you think of it. I'm seeing a lot of staring. Yes, Zach.
What's the domain of y? Is that just like a 0 to infinity?
The domain or the range?
The range of y.
Well, we know the domain, right, is from 0 to 1. So in this case, we can know what the range is here.
Okay.
Right? Because we know that we're only bounded from 0 to 1 at a time. Is that right? I guess we know. No, because that's fine. No, that's space, right? That's our space domain is 0 to 1. Yeah. Yeah. Right. So if you think about what we're trying to do graphically, we have 1 minus y, so we have that. Right? That's 1 minus y. What we're trying to do is add up sines and cosines so that we can, we have a sine like this, right? And maybe we have, double the period, etc. And we're going to try and put coefficients in front of those to add them all up, right? To see if we can't get a curve like that. That makes sense? Okay, so that's what Fourier series is. I just want to make sure. Okay, so now we have this. So what we need to do then is solve for these coefficients, right? We need to somehow find those coefficients. So let's work on that problem.
Dr. Tree, which one came first, the Fourier series or this solution to the differential equation? Or was it discovered through trying to work on this different?
So I don't know if this particular problem, but Fourier is a lot in heat transfer, right? And he's also in the math here, right? So I think these ideas were developed at a similar time, right? So I don't know exactly the history. It's a good question. Sounds like a trip into Wikipedia, like we could all spend an hour or two reading a little bit about the history of exactly how they came about. But these ideas were sort of discovered or developed together, right? Yeah. So let's say so. I'm going to rewrite this up here. So T y equals 0 equal to sum from infinity dn. Sine n y. That should equal 1. Okay, I'll write that like this. How are we going to solve for the dn's? Okay, that's what we're trying to find here. That's our unknown. So we need a second trick. So our first trick was superposition, right? We had lots of solutions. The trick said that if it was linear, we could sum them all up. That would be okay. The second trick also has a name. Okay, this is called orthogonality. So how can we find the d sub n? Okay. Okay, that's the answer. So I'm going to say a function, what do we call it, f, is orthogonal to another function, g, if the following is true. If I have an integral from 0 to 1 of f of x multiplied by g of x dx is equal to 0. Okay. So if that's true, if I have a function f and another function g, if this integral 0 to 1 f of x multiplied by g of x dx, if that's 0, then I'm going to say those functions are orthogonal. Okay, we're going to see in a little bit that this is an inner product of functions. Okay, we're going to talk about what that means a little bit more when we talk about Sturm-Liouville theory. Okay, so if I have this, I'm going to say that they're orthogonal. So we can use this trick to simplify this. If we can find a function that's orthogonal to sine. Okay. So it turns out we know. So what is orthogonal sine and pi y? Okay. Turns out sine is orthogonal to sine. So I do integral of sine of n pi y, and I have sine of m pi y dy. This equals 0 if m does not equal to n. Okay, if I take, one mode sine wave, and I have another one that has different period, okay? And I take the product and take the integral, that's 0, okay? You can, I'm not gonna do out the integral here, but you can go and do that, or you can plug it into Mathematica or whatever, and find out that that's true, okay? If, on the other hand, m equals n, okay, that integral equals 1/2. So that would give me sine squared n pi y, for example. Now it'll give me a 1/2. Okay? So I can use this trick and take the integral of both sides here, okay? And think what's going to happen when I do that. When I do that, when n doesn't equal m, I'm going to get zeros, right? So all of them will go away. This infinite sum will then go away, and I'll be left with only one case where m equals n. Okay, so let's do that. So if I take the integral of both sides, I'm going to have the integral of 0 to 1, and then I'm going to have the sum n equals 1 to infinity dn sine of n pi y. I'm going to put in here sine of m pi y dy. And on the other side, now I'm going to have an integral from 0 to 1 of 1 minus y multiplied by sine of m pi y dy. Like that, right? Okay, so I just took the integral of both sides and I multiplied by sine of m pi y on both sides. Okay, so now I can switch the sum and the integral if I want, right? That integral comes inside. Okay, dn is not a function of y, so that integral can move all the way to that spot right there. And that is exactly the same thing that I have right here. Right? So what I get out of that is dm over 2. Okay? And then on this side, I'm going to have an integral to evaluate. 0 to 1 of 1 minus y sine m pi y. Okay? Questions about what I did there? Make sense, Brian?
Yeah, so m, well, we're going to solve for what m is.
Yeah, we're going to solve for dm. So m is a subscript. Remember?
What is the sign?
In the sign.
Yeah.
So what this is going to tell me is that that coefficient depends on what m is. So m's not going to go away. Does that make sense? So m here is still, 1, 2, whatever, right? So there's a different coefficient for every part that's going to go up in here. Does that make sense?
Yeah.
Because that's what I want to find at the end. The problem with the m over here, if it didn't go away, if it wasn't orthogonal, was now I would have two indices. It's like a matrix as opposed to a vector, right? Andrew, you had a question?
At first I was confused where you got this equation with the 1 minus y on the right side, but you just took the original equation and multiplied it by sine m pi y and
Yep.
integrated.
Yep, exactly. Okay, yep. So I took that equation right there. Yep, multiplied both sides. Yep, and integrated. Yes.
And so this expression that we have here, this isn't solving for d sub t, this is just solving for the dm or dn.
Exactly.
You can plug
I
it
can,
back
I
in.
can relabel this, right? Like this is now a free index. I can call this dn if I want. I wrote dm because I wanted to show, that n equals m.
Yeah.
Right? But I can also call that, let's rewrite that. dn is going to equal 2 times the integral from 0 to 1 of 1 minus y sine. Now I need to put an n over here. dy, where n is equal to 1, 2, 1, ever, right? Okay, that's right. So what I'm trying to do is figure out what are the how much of the amplitude of each of those signs do I need to add up so that I can make it have a 1 minus y, right? So it's this, it's the answer to whatever that integral is. Okay, so now we can do the integral out. It's takes some u substitution, okay? So I don't really want to take the time to do the integral because I think you guys can either plug it into Mathematica or you can do the u substitution for yourself, okay? But that integral is doable. Yes, Andrew?
Sorry, just to double check. So dm is equal to dn, right?
Yeah, yep. All I did was just change the index, right? It's just notation.
Right. But here, we're only using the case where m and n.
That's right. Yep. Okay, so now I can do this integral. It doesn't use u substitution. Integration by parts is what I meant to say. Okay, so we have to do some integration by parts. So we'll just put that in. After integration by parts, we get following. We get that d sub n is equal to 2 pi by n pi. Okay, that's it. That's what we get. So 2 over n pi, 4 is equal to 1, 2, etc. Okay, so now we can take, now we found it. Now we found what n is, and we can take that, plug it back into our solution, and plug it back into our original solution, right? Because this one just tells us, you know, the initial condition here, okay? But now we can plug that back into our full solution. My phone. Why is my phone do that? On, not silent. Turn off. Why is my wife texting me in the middle? Okay. So let's plug that back in, and I'm going to write it over here. So we have bt at y comma t is equal to, and we should have an infinite sum, right? 1 to infinity. Now we need to put in a dn, which is 2 over m pi. And then we had what, exponential minus n squared y squared t and sine of n pi. Check. That's it. Yep. Okay. So now we solve for phi of t. We're done. Almost. Let's plug it back in and write out our final answer so we can do the rest of the little bit. So we said that, if you remember, I wrote up here phi of y of t is equal to phi infinity minus phi t. So phi infinity was 1 minus y, right? So we have phi of y t over 1 minus y minus that infinite sum. 1 to infinity, 2 over n pi, exponential minus n squared plus t sine of n pi y. Okay, let's do it right. Let me make sure. Okay, and then we can even now go back to dimensional units. If you remember, we said that Vx over V naught was phi, and we had y was equal to, we had y tilde was equal to y over b. And I think that was all we need here, right? Let's see, t was equal to what?
T over tau.
Yeah, it was t over tau. Tau was
Squared over nu.
b squared over nu, so that we should get that. Is that right? Okay, so let's write that one out. Make ourselves feel happier. Phi of y t in real variables, right? Maybe we go back here and put those on. So we remember that this is those were really real variables. Okay, so now, oh, we don't want to write phi of y t. We want to write Vx at y comma t, just divide by v naught is equal to 1 minus y divided by b minus the sum from n equals 1 to infinity by 2 over n pi multiplied by the exponential of minus n squared pi squared nu t divided by b squared, close brace, sine of n pi y divided by b. Okay, we're done. We did it. Okay. All right. Here's I got a picture of it. Yes.
Well, because I don't remember that well when we were for Friday, I'm a little confused by when we say phi of yg equals the steady state solution minus the time dependent solution.
Yes.
Because the steady state solution is 1 minus y. And the summation term we have being the approximation of 1 minus y. So doesn't that make phi equal to 0 everywhere?
If, okay. You're saying this is equal to 1 minus y.
Yeah.
That is equal to 1 minus y when that was 0, right?
Oh, yeah.
T equals 0. So that's what we want, is that at time 0, we want this to be 0, right? Because that's what we said the original initial condition was. Right, so we said it was initially nothing moving, and then we start the plate going. So, that makes sense?
Yes.
Okay. So let's make some comments. That's part E here. Okay, so the first one is lots of steps. Okay, I just gonna want to talk about the method. Okay, so these 5 steps that we did are the same, okay, for any separation of variables. You product solution, you separate them, you solve the time-dependent problem, you solve the space-dependent problem. Okay, there will always be one problem that is the time-like problem where you get where you don't solve for the CN, okay? You don't have the coefficients. And then there will be an eigenvalue problem, which was the second one we did, where you apply the boundary conditions and find the eigenfunctions, okay? So, but these same steps apply. And then in step 5, we have those two things. We use superposition and orthogonality, okay, to apply the initial condition, okay? So that is always the same process for separation of variables. Okay, so lots of steps, but always the same process. Okay. The second thing is this answer looks a lot different than maybe some of the answers we're used to, right? So this is an infinite sum. In a way, you might think that's not actually that useful of an answer, right? Like, you have to add up an infinite number of these things in order to know what the final solution is. Okay, that's kind of a bummer. So these series solutions like this are maybe less useful in a way than like the sort of closed form solution you can get without that. But it's still better than something you have to do on a computer, because you can write it down and you don't have to do some, you know, this you could just write in a loop, right? And you hope that if you truncate it, okay, so, you know, practically, we will truncate the solution for finite n, okay? And we hope it converges quickly enough to be useful, right? So if we have to keep 1,000,000 of these, that means we have to write a loop that goes 1,000,000 times in order to add that up. And then y here, that's a domain, right? That's a whole space. So that's going to be expensive. But usually, maybe we only need 10. Okay, maybe we only need 5. That's pretty good, right? That's maybe, an answer that's longer than I might want to write out by head with 5 terms, right? Where I put in, n equals 1, 2, 3, 4, 5 in there. Okay, but on a computer, that's pretty good. That's a lot better than doing a finite difference solution, right? And solving it as a function of time. It's a lot cheaper and more accurate. Okay, so I thought it would be interesting just to look at what the solution looked like. So let's see if I can put it up on the board here. I don't know if I do this, are the online folks going to be able to see the screen? Can you?
Do you want to just pull it down?
Yeah, let's do that. Let's do that. That'll be the easiest. Anytime. Any time of day. Just not on. It'll do that. There. Saw it show my computer. Ah, okay. So here is the transient only. So this is just phi t, okay? And so what you can see here is the dashed line is phi infinity, okay? And then phi t, this is a really short time. So even at a really early time, it has that sort of character. Like it's really hard to get it to go all the way to top up there, okay? Then as time goes on, that goes away. And here's our full solution right here. Okay, so this is the domain y, right? This is phi. So let's see. Oh yeah, you can imagine like, and this is early time, and that's infinite time. So this is sort of what the velocity profile looks like, going from at early time, just goes a little ways, right? All the way to late time, where it's now starting to flatten out and become. And what's kind of interesting is you can see, if you were to plot the solution we had last time at really early times, or plot the solution we did with the semi-infinite boundary, if you go to really early times, that solution will overlap because it can't see the far boundary yet. All right, well, that's kind of interesting to look at that. You can see the code here. I used to plot this. Maybe you can, maybe you can't. Let's do that. There it is. I was trying to get it to zoom in. I can't zoom very much. But you can see to do this, all I had to do was define a sum, and I used 21 modes, which was kind of a lot, but it's pretty fast and it was easy and it makes a nice clean solution. I could do it with something less and you could see, maybe that would be interesting to do. So let me pull up this and let me make it only 11. And let's see how many. That's not what I want to do. Run the solution. Open the terminal. Let me Python 3 plot solution. Okay, you can see with only 11 modes. This one. You can see that it's fine down here, but as I'm trying to get to this initial condition, it's struggling. So I have to add that up. That's because, you know, Fourier series, if you remember, they're sort of periodic like this, right? And so it has a discontinuity between here on this other side right there and up there, okay? And so it's struggling to resolve that jump discontinuity. So it doesn't converge very quickly on that jump discontinuity. So sometimes you can play with your solution and make it so that it is periodic. Like if you can change the way you subtract a transient or whatever, and make it so that your initial condition is periodic and then your solution. All right, so I just wanted to show that solution. Any questions about separation of variables?
I have a quick question about the graphs. So
As I take that.
I know, right?
My fault. Yeah, what's up?
the V infinity is time equals infinity, right?
Yes,
That was basically a straight line.
yes.
But the graphs that most closely fit that was really small, not really larger.
Oh, that was because you remember phi t, we wanted to equal phi infinity. The way we did remember that's kind of your same question here. You're asking why when that one equals 0, does this equal that part? Right? So the transient, we said, sort of, it goes backwards. We wanted to start out exactly canceling out the final solution and then going away. So in your mind, you're thinking of the transient part as like the part that's adding up to give the final thing. But what we did was we said, let's subtract out the end, and then we'll start with a negative end, and then work our way backwards.
Okay.
Does that make sense? Yes. Okay. All right. All right, we got 5 minutes left. We can start on Sturm-Liouville theory.
Three.
Yes.
I can see this separation of variables to be pretty tricky if we're changing up these functions a lot. When we have functions that are not going to be like sines, where we're going to have to figure out what's orthogonal to it or something like that.
That is a perfect question for leading into Sturm-Liouville theory. Alex. That is exactly where we're going. How did we know it was sines? What happens if it's not sines? What other functions are out there? Exactly. Great question. If I had a candy bar, I'd give it to you. So good. Okay. I'll just, after class, I know I set that up. So that's good. Okay. Because you're like, this is starting to, like, I have this feeling, this sinking feeling, Dr. Tree, that you gave us the easy problem with the sines and that there's other stuff going on behind the scenes here, right? Okay, so so maybe just to kind of summarize what I'm saying here is, so the procedure, the separation of variables procedure is actually really general. And I think I said before, if there's one technique to solve PDs that you ever had to learn, it should be that one, okay? And it will apply in a variety of geometries, and it'll give us a bunch of different kinds of functions. And so how are we going to think about that? How are we going to understand some of the depth of that, okay? So we're going to learn a little bit about the background of this theory. The caveat is that we could spend easily an entire semester doing what I'm going to do in the next probably 2 days. Okay, we could easily spend an entire semester on just this subject. There are entire courses taught at this university and at other universities about that. Okay, and one of my, like, the things I lament in our program is that we don't have a math, like a core math class that you guys take. That's part of the ChEn curriculum, okay? And at many graduate programs, there is one, and this is one of the main things that they cover, okay? So part of what I'm kind of trying to do here is like add 2 days of like, hey, this thing we just did isn't disconnected. There's some deeper math that we could understand, okay? And so I'm just trying to hint at that. So if this next little bit isn't your cup of tea, don't worry, I don't have homework on it. I'm not going to ask crazy hard exam problems on it. I'll probably just ask kind of conceptual problems from it. Okay, so I just ran out of time. So we got to there, okay? And we talked about the comments. And I'll just tell you the thing that we're going to do next is function spaces. Okay, so you can kind of chew on that and think of what does he mean about function spaces. And what I mean a little bit is when I talked about vector spaces earlier in class, this is a generalization of vector spaces to function spaces. Okay, so we're going to leave Andrew's question hanging in the air, and we're going to talk about that on Wednesday.
Couple days.
Okay.